Okay, so this lecture is going to be talking a little bit more about the kinematics of free fall and some problem solving. In this lecture, we're going to be reviewing what free fall is, what acceleration due to gravity is, and the fact that it happens anytime you're near the surface of the Earth. So remember that acceleration due to gravity is a vector, right? So it'll always point toward the center of the Earth. Always, every single time. When we talk about acceleration due to gravity, when we talk about this g value, we talk about it as the gravity at the center of the Earth, which is equal to 9.8 meters, 80 meters per second squared. So in order to follow along on this activity, you're going to need to take some notes. Alright, you're going to need some graph paper. I recommend that you have a calculator handy. And I'm also going to highly recommend that you have your phone, camera, and possibly an app download. And we're going to talk about that. So make sure that you have those materials. I'm going to have you guys recall your examples 2-10 and 2-11. So that means that if you haven't watched the previous lecture about acceleration due to gravity, make sure to do that, and maybe even keep your book handy on page 32. So now that we've gotten that stuff over with, let's go ahead and let's have some fun. I'm going to have you actually do an activity. Alright, and the activity is to grab a tossable object and toss it into the air and observe its motion. Now, when I say grab a tossable object and toss it into the air, I don't mean any old object. Alright, objects that have pointy ends, probably a bad idea. More like, say, a tennis ball would be a great object, or a fluffy little stuffed animal, preferably an octopus. Alright, and when you throw them in the air, make sure that you're catching it each time. Don't just throw it randomly into the air and wonder what's going to happen. You're going to throw it and catch it. So if you're not terribly coordinated, like me, for example, you might want to practice a couple times. And please, 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 make sure no sharp ends, no jagged edges, no points. Your parents would never forgive me if you took your eye out doing this activity. So what you're going to do is you're going to take the object and you're just going to toss it into the air a few times. Now, obviously in this example, right, I can only throw it so high, about 8 inches before, like that's how massive my hand is, before it hits this. So what you're going to do is you're actually going to physically toss it a few feet up into the air, maybe up to a meter up in the air. And you're just going to observe its motion. Because I can't physically be here for you for this particular experience, what do you know? I planned accordingly, and I actually had a friend of mine do a little bit of ball toss on video for us. And so that ball toss on video happens to be right here. Alright, so she's just throwing it up into the air and catching it. Alright, and that's our wonderful student teacher working with Ms. Motor over there. But that's all I want you to do, is I want you to just toss it in the air and catch it, and I want you to observe the motion. Alright, do it a few times. And I want you to think about, how does the object's position change? And don't just tell me, well, first it goes up and then it comes down. Right? We know first it goes up and then it comes down. I want you to think about, how does it go up and how does it come down again over time? right? Is the position changing in even increments? Is it rapidly going up and slowly coming down? Right? So I want you to think about that, and I want you, as you think about it, to sketch the graph of position versus time of that object. And I read your mind already. Those of you that know that I have a graph of that position versus time change underneath this blank sheet of paper, too bad. I mean, like, seriously, just sketch it. Doing it yourself, making guesses, maybe even finding out that you're wrong is how you learn, and you're going to be turning in these notes, so I'm going to be able to tell if you copied my graph or not, because let's face it, whatever you sketch might not be perfect, and you're probably going to have to sketch my graph anyway, so I'm going to know whether or not you actually followed the instructions and made the attempt to sketch the graph. Before I actually show you your position versus time graph, I'm going to bring up that thing I talked to you about, which conveniently I have planned under here. It's a really neat app. Really neat AP. I'm so cute. It's a really neat app. And it's called Video Physics. And I highly, highly, highly recommend, if you have any ability whatsoever to get Video Physics, just do it, right? Beg your parents, tell them, oh, I need it for school. All right, here's my Video Physics right here, and you're gonna notice that in my Video Physics, I already have this particular situation uploaded. So you could take a video and you can analyze it. So we could just play the video, right? It's the video that I just showed you. And I asked you to think about, well, how does the ball's motion change while it's in your hand? And so we're going to zoom in on this situation. We're going to pretend like there is no glare. Right? And what we're going to do is we're going to just consider the ball once it leaves her hand. So right about there, we're going to consider, what is the ball's motion as it travels through the air? So what does the ball do? Well, first it's there, and then when I click that point and I mark that point, it allows it to jump forward a fraction on the video. Well, then it's there. And then in the next second, it's there. And then the next second, it's there. And in the next second, it's there. And in the next second, it's there. And then the next second, it's there. And then the next second, it's there. And in the next second, it's there. And there. And there. Now, let's consider something. If it's difficult to see, I'm sorry. I do my best. But you could take your own video and you could look at this also. What you're going to notice is that, how did the position change? If this video is moving forward an equal amount of time every time I put a point down, then how is it changing as it goes up into the air? All right, first the position changed this much, and then this much, and then this much. And you're going to notice a pattern that as the ball went up into the air, it started covering less position with every time interval. Alright, so what does that sound like? Alright, as the ball left the origin, it was traveling up, but as it traveled up, it began to cover less and less position over time. Less position, less displacement over time means a smaller velocity, which means a smaller slope over time, which means that, oh, it's a decreasing. All right, this is what do we call it? A soft curve, I think, right? We call that a soft curve. All right, it's an exponential relationship, we think, that created that soft curve. Well, let's continue to focus on what's happening. Well, as time goes by, right, now the ball is making its way back down and down and down and down and down, alright, until it hits her hand. And once it hits her hand, it's no longer in free fall any longer. But now we could take a look at those points that it came down with, right? And what do we notice? Well, at first it was barely covering any position over time. But then, as it continued to fall, it started covering a greater and greater amount of displacement over time, which means that up here at the top, it started with a soft curve that gave us a steeper and steeper slope. Alright, so that means that, well, here is what our position versus time graph should look like. It should look something like this. Right? That represents this motion. Right? Here we're just marking position. Right? We are just showing this position. Oops. Sorry guys, I'm trying an awesome experiment of moving around where the focus of the video is, so if things jumped around a little bit, don't freak out. That was me, not you. But that's what we could see, right? And if I go back in the video, right, and I frame by frame, we skip forward and we watch it, we can see for certain that every single second that passes by, or every single fraction of a second, it did hit each of those points. So this did happen. Alright, that is our position versus time. So now, you didn't see anything. Now that you have your position versus time, and I have no focus on this, we're just going to bring that back in there, and we're going to try to focus again. We're going to give it some earth to focus on. That usually helps it, because gravity is a vector quantity always pointing toward, that's right, the center of the earth. So if you were in space and this were your frame of reference, gravity would be pointing that way, toward the center of the earth. But now we have our position versus time graph. And I'm going to ask you to use that position versus time graph and figure out what does the velocity versus time graph look like. No peeking. Alright, the velocity versus time graph. If we're going to consider our position versus time graph, this guy right here, how is velocity changing as the ball goes up? How is velocity changing as the graph goes down? Well, let's consider our slope. First, right here, we have a positive slope in the positive direction. And that positive slope in the positive direction is decreasing in its size. And then toward the top, it actually levels out till there's no slope. And then, as it changes directions from a zero velocity to a very small negative velocity to a very large negative velocity, well, what would that look like? Right? From my perspective, I want you to draw it. Seriously. Push yourself. Draw it. And when you're ready, you're going to take a peek. Because I said it started with a high positive velocity, right? A high positive velocity, a steep slope, right? And that velocity slowly decreased in a steady manner until it was zero, right here at the top. That's a velocity of 0 right there. Then, from 0, the ball began to fall, which means that it was moving back toward the original position, in the negative direction until it was a very large negative result, which means this is our velocity versus time graph. I want you to do your best to do what I just did. Describe it. And I also want you to take a look. Here we're back to Video Physics app, which seriously, if you can in any way, shape, or form get a hold of this app, I strongly, strongly, strongly encourage you to do it, because you can use it when you're designing your own labs. You can use it when you're analyzing problems and situations. So what we're going to do is we're going to set our scale. Right? We're going to say that that's the x direction and the y direction, and we're going to set it to about 653 pixels. 604 pixels will equal 1 meter. We're going to take a look at the graph, and this is the position in the y direction as it traveled up a little over a meter, and then it fell nearly straight down. That's position versus position. What we're more interested in is the position versus time. Right? Over time, right, the position changed in the positive direction first, but it changed at a decreasing rate. Right? There is a larger change between point 1 and point 2 than there are between point 9 and point 10. And then there's a very small to almost no change between point 11 and point 12 versus 21 and 22. Right? This is our position versus time. And what we can see is that it is a parabolic function, just like we predicted it would be. And then we look at our velocity versus time. I know you can't read the words, but that's what this is. It's our velocity versus time. And what we see is that, with the exception of maybe our first and our last points, where it's difficult to see in the video unless we break it down even more, whether or not the hand is actually touching the ball toward the very beginning and very end. But if we look at that midpoint, we notice, right, we go from a high positive velocity to no velocity, from no velocity to a very high velocity in the negative direction, and that is a smooth slope. So we can prove to ourselves the slope of a velocity versus time graph is meters per second per second. So that means that the slope of a velocity versus time graph is acceleration. I just want to let you know I wrote that word without looking at the paper. So we have that definitively here. We have actually analyzed a real-life object, and we've plotted its motion over time, and these are the real results of this motion. So now it's time for you to do some plotting. Oh, you thought your graphing was done. That's cute. All right. We've done position versus time. We've done velocity versus time. We've talked about the slope of the velocity versus time being our acceleration versus time. So that means create acceleration versus time graph. And I'm just going to remind you that this is our slope for our velocity versus time. So if this is our slope for our velocity versus time, that to me appears to be a fairly smooth curve or smooth line, which means that it's the same slope all the way across, which means it's the same acceleration all the way across. So when you draw it, a drum roll please, should look like this. Do you feel like a genius yet? All right, your acceleration was negative. All right, and we know it's negative because look at that slope. That is a negative slope if I've ever seen one. And It's the same the whole way through, so that means the acceleration is the same a whole way through. Gee golly, Miss B, I never thought I could feel so smart all in one little video lecture. So let's think about things that fall. We're going to take a break from tossing objects. So take your preferred tossing object and set it aside. And what you're going to do is we're going to be like Galileo. Oh, where is he? Here, Galileo. There he is. We're going to be like Galileo, and we're going to simplify the situation. All right, we're going to say we're going to consider a situation where we don't have to worry about air resistance, and where we're near the surface of the Earth. And remember, when you're near the surface of the Earth, we can say that gravity has a value of 9.8 meters per second. Now that we've considered those things, you're going to fill this spot. And I have points showing from 12 to 13. You're going to do times 0 through 30 seconds. So that means that's right, on top of all of these values that are showing here, you're going to go all the way to 30 seconds on your graph. So if you're the kind of person that has to set up your graph before, that's right, stop now. Your x-axis is going to be time in seconds. Better be done with a ruler on grid paper, not like this, Miss Bjorklund. And you're going to create your 0 to 30 second margin with individual time points. You're going to do this for position versus time, velocity versus time, and acceleration versus time. So let me give you a paper breakdown. Let's pretend that this is your piece of graph paper. Let's be easy. Right? If you're going to do one side, they'll make this the position versus time side. Here's your velocity versus time. And then you'd flip it over. And on the back, your acceleration versus time. Alright, so that means the piece of paper that you're going to bring in complete is going to have all three graphs on it. I'm going to know. I'm going to know if you did this or not, because yes, you're submitting your notes online, but you're also bringing in your completed graph. And please submit it with your notes, right? I want to make sure that I can give everything all one grade in Canvas, but bring it to class. So, we're just like Galileo. We're simplifying the situation. How are we going to get these values? Well, I'm going to give away something. This is a falling object. So remember that example 210 gave us the note that whenever we say an object is dropped, we mean that the initial velocity is 0. So this is a dropped object. The initial velocity is 0. We're going to, in our frame of reference, we're going to set its starting position as 0 meters. A velocity of 0 meters per second. Do we know, once the hand lets go of the object, what the acceleration is going to be? I'm listening. That's right, you should have said it was the acceleration due to gravity. We have to establish a frame of reference. Right? Our frame of reference is Earth, but more specifically, since gravity is an attractive force that always points toward, that's right, I heard you say the center of the Earth. We're going to say that downward is the positive direction, so that means that I can give my acceleration a positive value of 9.80 meters per second squared. Now, I want you to tell me, does the acceleration due to gravity ever change while this falling object makes its way down toward the center of the Earth for 30 seconds? If I tell you that it can fall for longer than 30 seconds, nothing in its way. I'm listening. I'm hearing you say that acceleration due to gravity will not change, and you're so right. It's going to be 9.80 for every single second. Alright, and it's meters per second squared. So you're going to fill out 9.80 meters per second squared for all 30 values. because we're neglecting air resistance. So that's not the only thing that we can recall from example 210. There's a few more exciting little tidbits of information that we can pull from example 210. The first one is, if we're going to determine the position for every single second, we could use this equation. The position is equal to the initial velocity times time plus 1/2 the acceleration due to gravity times time squared. And our initial velocity is 0, so we can calculate that, right? The position is going to equal 1/2 gt squared. And we can do that for each second. And you're going to get some pretty nifty values here. You're going to get 1/2 9.80 times 1 squared is going to be 4.90 meters. And then we're going to get 19.6. I think 19.62 meters. That's just 19.6 meters. And we'll do this to 1 decimal place. We'll do this to the 10th place. And then after 19.6, we get 44.1 meters. And then 78.4 meters. And the rest is up to you to fill out. Remember, all the way to 30 seconds. And we could do the same with the velocity, right? The velocity is first 9.8 meters per second, right? Oh, how did I do that, you might ask? Well, remember an example of 2-11 when it said that the final velocity in any situation with uniform accelerated motion, like falling, is the initial velocity plus gravity times time, and our initial velocity is 0, so that just means that our velocity is going to be calculated as gravity times time, because this is a uniform accelerated motion situation. So the initial is 9.8, and then 19.6, and then 29.4, and then 39.2, and the rest is up to you to calculate. Remember, all the way to 30 seconds. And once you've calculated that, you're going to plot the data, position versus time, velocity versus time, and acceleration versus time. Once you have them graphed, I would like you to write a comparative paragraph. Compare it to our conceptual graphs, right? And when I say our conceptual graphs, I'm talking about these guys of the actual situation. And I also want you to compare position versus time to velocity versus time to acceleration versus time. Write it out. I want 1 to 2 paragraphs. I want you to describe the relationships. I want you to describe the motion that created them. And please upload it with your notes. I will put a grade on it, but bring them to class ready to go.